Hello all, welcome once again to this course Electric Vehicle Dynamics and Motor Drives. And in this module, in this segment, we are basically discussing the modeling and control of various AC machines. And we have seen the modeling and control of permanent magnet synchronous machine, and we have proceeded with the modeling of the squirrel cage induction machine. So in the previous lecture, we have seen that we can use the generic equivalent circuit to define some of the flux and inductances which are associated with the machine. So we are defining on basis of the available circuit elements which are there in the picture. So we have leakage inductances and magnetizing inductance available over there, and we are defining the air gap flux on basis of the current passing through the branch LM and the value of magnetizing inductance. So that is defined as psi m. Now going ahead, it is suggested that the total stator inductance can be written as sum of the leakage and magnetizing inductance. And at this point we have defined a term which is called as stator leakage coefficient, and this is ratio of the stator leakage inductance and magnetizing inductance. So hence we are able to express the value of stator inductance in terms of magnetizing inductance and stator leakage coefficient. Similarly, we have also defined the rotor inductance, and we are defining the term rotor leakage coefficient, where it is used for correlating the rotor inductance and magnetizing inductance. Now, once we have defined the inductances, we have gone ahead to define the flux associated with the machine. So first one, we have the stator flux psi s, defined as the sum of magnetizing flux and the stator leakage flux, and this can eventually be expressed in terms of inductances and current associated with the each branch. And we are defining the stator flux in its native frame of reference, and therefore we have superscript given for the rotor current. Altogether, we are coming up with a term which is combination of stator and rotor current and stator leakage coefficient, and this term is basically defined as the stator flux magnetizing current IMS. And we are saying the stator flux is nothing but product of magnetizing inductance and stator flux magnetizing current. So this simplifies the representation of stator flux in the induction machine. On the similar lines, we have gone further to define the rotor flux, which is basically sum of the magnetizing flux and the leakage flux on the rotor side, and we have introduced the corresponding terms in terms of inductance and the current. And because rotor flux is the quantity which is associated with the rotor frame of reference, we are having the stator current given with a superscript R. And once again, by taking out the LM from the complete term, we are able to express an equivalent quantity which is called as rotor flux magnetizing current, which is again combination of rotor and stator currents and rotor leakage coefficient. And this can be used for defining the rotor flux as product of the magnetizing inductance and rotor flux magnetizing current. So therefore we have another compact way of describing or compact way of representing the rotor flux. And when we are going for the modeling, we are going with the DQ frame of reference or synchronously revolving frame of reference, which is basically oriented towards the rotor flux. So which means we are talking about the frame of reference which is going to be aligned along psi r, and that is what we have done by showing all the three frames of reference over here. So we have a stationary alpha s beta s frame of reference which is attached to the stator. We have alpha r beta r frame of reference which is attached to rotor, and because this alpha r beta r is attached to rotor, it is rotating with the speed omega m. Then we have a synchronously revolving frame of reference DQ, where the alignment of psi r is along d. That is what is our requirement, and this dq is basically revolving with the speed omega s. So the angles formed by these frames of reference are given as epsilon and rho. So epsilon is between the alpha r beta r and alpha s beta s, and rho is formed between dq and alpha s beta s. So we have correlation between the angle and the rotational speed as given over here. So on basis of this, we can also define our slip speed, which is basically the difference between the synchronous speed and mechanical speed, and this is rate of change of the angle between the alpha r beta r and dq. So once we are clear with the definitions of the frames of reference, then we can go ahead with the generic equations which we have derived for cylindrical rotor multiphase machines, and we can write the KVL equations for the stator and rotor side. And what we find that, because in particular we are dealing with squirrel cage induction machine, so essentially the voltage at the rotor terminals is going to be zero. It is shorted at the terminals. So which means that the equation what we have on the rotor side gets slightly simplified because of the presence of zero vector, and there is another condition that IR cannot be measured because many times it's closed circuit and then we do not want to introduce any extra element for measurement or anything, and rotor bars are associated over there. So we would like to have a representation of IR in terms of quantities which can either be measured or it can be estimated, and this is where we make use of rotor flux magnetizing current IMR, and we express IR in terms of IMR and IS. Once again, to confirm this, that IMR is represented in the rotor frame of reference, which is why we have superscript only given with the stator current IS. Now going ahead, we have replaced the rotor current with the appropriate value, and then we are finding that the whole term can be simplified in terms of the real and imaginary components, and eventually it leads to DC quantities in the synchronously revolving frame of reference, where the first equation correlates the rate of change of IMR with the difference between ISD and IMR and divided by TR. So essentially it suggests that IMR is basically generated out of ISD as if there is a low pass filter connected after ISD. So this is the flux model for the machine. So in terms of current, we are able to realize IMR from ISD by having a low pass filter, and the response can be seen over here. If there is a step change in ISD provided, then we can have IMR going like this red waveform. And the second equation for this same derivation, it correlates the slip speed with the ISQ and IMR components. So ISQ on the other hand is basically representation of the torque component of the current, and which is why the loading defines that how much slip speed we are going to encounter in the machine. So higher is the loading, which means higher is the torque, and that is going to reflect on the slip speed, so higher is going to be the slip speed magnitude. We have also seen the phasor diagram for the induction machine in motoring mode, where we have also tried to draw the stator and rotor flux, and we have tried to see the relative positions of stator and rotor flux in case of machine operating in motoring mode. So going by the usual representations, we have drawn the psi-m and relative positions of ES and ER, and then on basis of IR we have drawn the stator current vector, and then on basis of that, by using the additional terms with the psi-m, we are able to draw the stator and rotor flux, and the angle between them can be called as load angle or torque angle. So higher the value of load torque, higher will be the value of delta. Now going ahead, we'll be using the second equation from the general model, which means the stator side KVL, which is represented in the stator frame of reference, and once again it consists of rotor current given in the stator frame of reference. Now, because of the aforementioned constraints, IR must be represented in terms of quantities which can be measured or estimated. So we have defined the rotor current in rotor frame of reference in terms of IMR and IS by this equation. So here we have 1 plus sigma r. Now, because we are talking about stator frame of reference, we need to transform this equation to stator frame of reference, and that can be and basically this reduces to IMR represented in the stator frame of reference minus IS divided by 1 plus sigma r. So this can be used for replacing the IR current in the stator frame of reference, and the equation can be modified as now. Once again, we have written the equation in stator frame of reference or stationary frame of reference. However, we would like to transform these quantities to synchronously revolving frame of reference, because eventually our controllers are going to operate corresponding to the DC values of these quantities. So, taking the corresponding transformation to DQ frame of reference, we can once again check the frame of reference for quick reference. So we are trying to have representation of quantity which is there in alpha s beta s into DQ frame of reference. So we are trying to replace Vs with Vs represented in DQ frame of reference. So which means we are jumping on the clockwise direction. So it can be written like this. And similarly, all other quantities can also be represented in this manner. So we have the unit vector e raised to the power j rho appearing in the equations. Now the last term can be opened because there is a term related to the stator current and there is another term related to stator current at this position. So we can combine these two terms. and we can write this in a compact manner. Further, we can expand the derivative terms. So I'll use the second line for writing the other term. So now what we can see over here is that we have this term common everywhere, so it can be cancelled on both the sides of the equation, and we have the remaining terms given in the dq frame of reference. So Vs dq coming equal to Is dq Rs plus Ls minus Lm by 1 plus sigma R ddt of Is dq plus j omega s Is dq, and the remaining two terms over here. Now there are two terms which are coming related to inductance, one over here and one over here. I mean, these terms are repeating. So we can write these terms in little bit more elegant way by defining another coefficient. So we'll take this equation forward after having one more definition. So we can define a term which can be called as total leakage coefficient. Can be defined as sigma. So kind of similar term what we have defined for the stator leakage coefficient, rotor leakage coefficient. This one is combining basically the stator and rotor leakage coefficients, and this is essentially given as 1 minus 1 over 1 plus sigma is 1 plus sigma r. Now this term can also be seen as 1 minus Lm square by Ls Lr. So either ways this term can be seen. Now if we observe this term over here, Ls minus Lm by 1 plus sigma r, we can take out Ls and then we end up having, so we can multiply Lm on numerator and denominator and we can reform the term in this manner, and this now can be written as sigma. So Ls minus Lm by 1 plus sigma r can be written as sigma Ls. So it's a more compact representation of the term what we have over here. So this same is applicable to the next term over there. Now one more factor which is there written as Lm over 1 plus sigma r, this can actually be written as sigma r, and so we can see the value of sigma inserted over here in 1 minus sigma term, and this can come down to 1 plus sigma s 1 plus sigma r, essentially having as Lm square divided by Ls and Lr. So if we observe this term Lm by 1 plus sigma r, we can essentially multiply Lm and Ls on in the numerator and denominator, and we will end up having Ls times of Lm square by Ls Lr, and this can be written as 1 minus sigma times of Ls. So in this manner we can replace all the inductances in terms of the stator inductance and the total leakage coefficient. So the equation which is given over here can be written in a little bit compact manner. So we can replace the corresponding terms and we can write the equation in a much more compact manner. Now it should be noted that we have defined these quantities in DQ frame of reference with their respective coefficients. And IMR, which is actually aligned along D axis, so it has only real component which is IMR, the magnitude itself. So then we can take out the real and imaginary components from this equation and we can write the D and Q terms separately. So third equation is corresponding to the real terms which are taken from this equation, and fourth equation can be written for the imaginary component. Now, once again, it is interesting to note that the stator inductance is coming along with the total leakage coefficient sigma, which means that it is not corresponding to only leakage or only the total stator inductance. It's basically a combination of all the inductances which are present in the induction machine. Then we have cross coupling terms available on account of the axis transformation, and for the d axis we have a term which is present only during the dynamic conditions. So as long as IMR is settled, we will have zero value for this particular term. However, for the q axis, we have a term which is always non-zero, and it kind of correlates to the back EMF of the PMSM machine what we have seen. So we have the term representing flux, we have a term representing speed. So the combination gives a feeling of as if there is a back EMF produced in the induction machine. So these four equations basically provide us, I will write down the first two equations also for convenience. This was our first equation. Second equation which correlates to slip, and third and fourth. So these are the equations which correspond to the electrical model of squirrel cage induction machine. Now going ahead, we also need to derive the mechanical model, and for that we need to have understanding of what is happening with the torque, how the torque is generated in machine, and how it can be represented in terms of the quantities which we have included in our derivation. So once again, we need to take help of the phasor diagram, and we need to represent torque as a cross product of flux and current. So we have indicated that psi m and IR are interacting to generate the torque in the machine. The fundamental torque in the machine is generated by this interaction. So we can take a constant and we can take the magnitude of the cross product of psi m cross IR, and we can as well take the vectorial representation of these quantities. For convenience, we can define the quantities in the stator frame of reference. So for having the clarity of where we are going to express these units into. And then because psi m is eventually represented in terms of IS and IR, and IR is represented in terms of IMR and IS. So we can always replace these quantities with the quantities which are again measurable, or we can derive it through the measured quantities. So eventually we would want our equation to be realized in terms of IMR and IS. IS can be measured and then IMR can be derived from that. So replacing one by one we can replace, and we can end up having the cross product of IS and IR, which is again interesting to see that we had the interaction of flux and current generating the torque, but here we have the interaction of stator and rotor current, which is again generating the same torque. So we can have different combinations between the quantities which can develop or generate the same torque. Now because IR, again we need to get rid of this quantity, so we can replace it by this equation, and we will end up having and once again when we open the cross product, IS cross IS is going to be 0, so eventually we end up getting IS cross IMR, and all represented in the stator frame of reference. Now it should be noted that because we are more familiar with quantities which are expressed as real and imaginary components of a vector, and then when we are trying to have the cross product, we need to have the angle between them rather than having the components of the current and other quantities. So we would like to have appropriate replacement of this cross product in terms of something else which deals with the vector. So the cross product between two vectors, for example vector A and B drawn over here, so there is angle theta formed between the two. This cross product can as well be represented by imaginary of the complex conjugate product for A and B, and we are trying to equate the magnitude, so we are not worried about the sequence at this point of time. So this is how, and we can see that with simple calculation that these two will end up with the same expression. Torque as well can now be represented as the imaginary of product of IS and complex conjugate of IMR. Now IMR in the stator frame of reference can be opened up. The representation what we had given in the previous lecture, magnitude times of unit vector, and then we can apply the conjugate, and we can take out the unit vector, and it can be clubbed with the stator current for the transformation of stator frame of reference to DQ frame of reference. So this can now be seen as the imaginary of IS in DQ frame of reference times of IMR. Now if we open this ISQ in DQ frame of reference, we can denote it by ISD plus J ISQ. So we can find easily that the imaginary term corresponds to product of ISQ and IMR. And hence torque can be represented in terms of the rotor flux magnetizing current and the Q axis stator current. So this is where we are also capable of seeing that now, that ISQ is a quantity which can be responsible for changing torque quickly. We understand that there is a rotor time constant involved with IMR. Therefore, IMR is sluggish in nature compared to ISD and ISQ. So, which is why many a times when we are asked to change the torque in the machine in vector control, we naturally we choose ISQ for doing that. And by keeping IMR constant, we maintain a good value of the flux and then play with the value of ISQ to achieve the torque, the desired torque in the machine. Now, the value of constant can be taken as 3 times of P by 2. As a matter of exercise, it can be taken as a derivation, no, on your own, and it can be done. And for quick reference, the value of K is provided over here. So torque expression altogether can be written as so the factor other than the currents can be written as KT, and we have torque given in terms of KT, IMR, ISQ. So this gives us the electromagnetic torque generated in induction motor. Should be noted that it does not restrict us from representing torque as a product of any two vector quantities. For example, as a cross product of psi s and psi r, what we have seen in our phasor diagram for the motoring mode. We have defined that the angle between the rotor and stator flux can be called as load angle. So we can as well simplify and see that the cross product of psi s and psi r actually boils down to the same expression what we have started with, psi m cross IR. So therefore any two quantities can be picked up and cross product can be taken to realize the expression for torque. Now moving ahead, we can add the fifth equation to the model which corresponds to the mechanical model of SEIM. And this again can be written very similar to what we had for the DC motor or the permanent magnet synchronous motor. Where J is the moment of inertia, omega m is the mechanical speed in mechanical radian per second. We have electromagnetic torque derived as kT times of IMR ISQ. Tau L is the load torque, B is the frictional coefficient, and omega m once again the mechanical speed in mechanical radian per second. So these five equations together can be used for drawing the model of the machine, and on basis of that we can have appropriate controllers for controlling the speed and torque of the machine. So going ahead, let us try to draw the block diagram for this machine. So we have the D-axis voltage generated from the inverter, and there are a couple of terms which are getting subtracted. and the RL model for the electrical system, which consists of RS and S sigma LS, which is eventually generating our D-axis current. Now, the D-axis current is basically fed to the rotor flux model, and this essentially generates the rotor flux magnetizing current. On the other hand, we have the Q-axis block diagram. Once again, the electrical model remains same, and we have ISQ current generated after that. Now, the ISQ current basically interacts. So there is a product term with the IMR and again KT to generate the electromagnetic torque, which from which basically the load torque is subtracted and the resultant is fed to the mechanical model of the system. And this results into the mechanical speed. So for keeping uniformity, we can have all the speeds given in electrical radian per second. Now, once we have the mechanical speed, we do need to generate the synchronous speed of the machine, and we can use the slip equation for this purpose. So we have ISQ divided by TR, and once again divided by IMR to generate omega slip, and here we are adding the mechanical speed to realize our synchronous speed. So in total we have the model of induction machine in the synchronously revolving DQ frame of reference given like this, and because we are generating our voltages from inverter, we need to have the model for that as well. So inverter can be modeled as a simple gain by ignoring the delay term in the inverter model, and we have corresponding reference signals given as VSD for the D axis and VSQ for the Q axis. Now it can be seen that the torque is basically resultant of ISQ as well as IMR, or in other words, any change happening in torque, we must ensure that the flux and ISQ, these both the quantities are considered equally. And then we have slip speed generated on account of the interaction of ISQ and IMR again. So one way of controlling the induction machine could be is that we maintain the value of IMR at a fixed level and then change the value of ISQ as per our requirement. So we will not be interacting or we will not be disturbing the model which consists of another lag in the system or another delay in the system corresponding to the rotor time constant. So we will be using the quantities which are the components of the stator current in the induction machine. So design of the controllers and how to achieve the desired performance will be taken up in the next lecture, along with the terminologies which are related to the sensorless vector control of induction machine. Here we will stop with this model. Thank you.